So let's take a look at some additional equations for B, and we're going to start by looking at the divergence of B, looking at the curl of B, and Ampere's law. The divergence and curl of B leads to two of Maxwell's equations. It'll come to max E3, max E4, and this max E3 implies Ampere's law. It's a very useful law, of course, because you can look at B field tends to be for high symmetry systems. So to remind you, first of all, how to say BO Savar, think of BO Savar as the pronunciation of these names. You recall when we developed the BO Savar law, we had to have the definitions of the vectors similar to for electrostatics. This time the source is a little line element on a curve C where the current I is passing in this direction, and the position of that little vector is given by R prime. This would be like the source point for electrostatics. The field point P is given in terms of the position by the position vector R. And all of this is relative to the origin. Normally what you have is a physical effect that depends on this vector here, and that's our funny R. So sometimes it's called delta R, sometimes it's called funny R, and of course what it is equal to is R minus R prime, which is this vector right here. And to repeat, dl prime is an element of displacement along the wire. R funny R is the vector that goes from that little displacement to the point P. BO Savar for a current says in differential form, and keeping track of the vectors R and R prime, that the differential of B is given by this coefficient times dl prime cross funny R hat divided by R squared. Sometimes remember rewrite R vector and then put a cubed here. Same thing. And we've already defined funny R. Now the current density is related to the current as follows, that if we can simply write I times dl prime, that will be equal to the current density at R prime times the volume. So this is the volume current density times a d tau, say. dA is a differential of area normal to dl prime through which the current flows. And so we'll set that equal to d tau prime, which is the volume element through which J flows. And so we just replace that and get our differential of B. Remember, that's evaluated at the field point, is equal to mu 0 over 4 pi, and then we put in our current density crossed into R hat over R squared, and then that's times d tau prime. So that's our little differential in terms of a current density and the position relative to the origin and the source point. Integrating this will give us B of R, and so this is integrated over the whole volume that contains this current density. If we integrate all those little pieces of volume where we might have current density, then we'll get the B of R. Let's take the divergence of this B. So I've just repeated the equation for B up here, and we're going to take the divergence of both sides. So we'll have del dot B here, and I've taken the liberty of taking the del operator or the divergence operator and put it inside the integral. So we have the divergence of this vector here, and then we integrate over the volume just like we did up here. Now it's some bumping and grinding, so we have to have a product rule to simplify this. If we remember, this is equal to B dot the curl minus A dot the curl of B. This is the curl of A. So just simply taking this divergence here of a cross product, this cross product here, we can identify then that the A vector is J of R, and the B vector is R hat over R squared. So putting that into our product rule, we end up with this vector dotted into this one, this cross product, minus the vector J dotted into this cross product, all integrated over the volume. So let's see if we can simplify this, and the first thing to notice is that this operator here is taking derivatives with respect to x, y, and z. This vector over here simply depends on r prime, so x prime, y prime, z prime. There are no x, y, z's here, When we take this curl, we end up with 0. Earlier, we had worked on the divergence and curl of this particular vector here, and we showed that that was equal to 0. We have two terms then in our divergence of B that are factors which are 0. And so consequently we conclude then that del dot B is equal to 0. And this is the third Maxwell's equation. It's analogous to the divergence of E, except the divergence of E had a non-zero value wherever you had charge. Remember, this was a charge density. It could be thought of as a distribution of electric monopoles, in other words, charges. Del dot B equals 0 implies there are no magnetic monopoles. By the way, if you discover one, let me know, because it's a Nobel Prize. It also means that B cannot end or start from a point in space. On the other hand, if you remember, if you have, say, two charges plus minus, you could have field lines that go from one to the other and start and terminate at those charges. With B fields, you cannot have that. And so B fields, let's take a simple case, might be something like a circle that closes and has no source or ending point. So that's quite a bit different property of B fields versus E fields. Taking the curl next is a little more complicated. We do the same thing. We take the curl of B, and taking that same equation for B in terms of the current density, we bring the curl operator inside the integrand, and so we just simply have this equation here. We're going to use another product rule, which you remember we derived, but a little more complicated, and that's the curl of a cross product, and it's given by this four-term expansion or product rule, where you have various dot products of, say for example, B with an operator, A with an operator, and then A times a divergence and B times a divergence with appropriate signs. We boldly go on, so we take the product rule and just expand this quantity here, and keeping track of A and B again, we have our coefficient in front, and then here term 1, term 2, term 3, and term 4. And I think if you keep track of the vector J and the vector r hat over r squared, you'll notice that this is B and this is A. And so just putting those all into this expansion here, we can rewrite the curl of B in terms of this integral over those four terms. We pull the same trick that we did before in terms of the del operator. This is a operator on xyz functions. This is a function of r prime only, so this ends up being 0. A similar argument takes this term out, because here we have a divergence of j r prime. This is xyz operations, and so that equals 0 for the same reason. So that gets rid of two terms. So here's what's left. We have then to think about the possibility of simplifying these terms. The first thing we want to recognize is that these two functions here have components of the form x minus x prime. So for example, the r vector is consistent of this times a x hat, and then this times y, and this times z, and so on. So we have to think about then how to take derivatives of such a function. Let's just take the x component. If we have a function of x minus x prime, and we differentiate it with respect to x, then we can expand that and show that minus the partial with respect to x prime operating on this function with a minus sign gives us this equality. It's based on the fact that you have this minus sign here, and that brings the minus sign out here. Applying that then to the function that we have here, we're taking derivatives of a function of x minus x prime and so on. So to do that then, we're going to switch the operator in xyz to an operator in the prime coordinates, so x prime, y prime, z prime. So all we've done is this transformation here where we looked at one component, and this is for all components. The minus sign, in this case here, we have a minus sign up here. Here's the minus sign from above. And then when we put in this minus sign, after we've done this transformation, we end up with a plus term. So let's go back to examining the x component of this quantity here. So we're now talking about the first term of the integral, and we've already converted it to this form here, and we're only taking the x component of our r. Realize this is r hat over r squared, but that's equal to r funny r vector divided by funny r cubed. Sorry, that's what this is here. That's where the 3 comes in. If we look at the expansion of a operator and a vector, so vector dotted into the del operator, so that's what this is here. If we have it operating on a function, and by the way, this is a scalar function, this thing right here, so we'll just call it f again, then that's easy. That's just jx partial f with respect to x and so on. This would be the expansion of this whole thing in terms of x, y, z components. But if you look at that, you can see that it is equal to the vector j dotted into the gradient of f. So that's what we end up with, that j dot the gradient of f is equal to this operation here. We have to use product rule 5 to change this again. So what we're going to do is the divergence of f times a, of a scalar function times a vector, is equal to the sum of these two quantities here. This was an identity that we derived earlier. What do we have up here is this term here. And so we solve for that, which is a dot gradient of f is equal to the divergence of the product, which is what we started with, minus the function times the divergence of a. So putting that product rule into our function up here, so here's what we've got up here. We put all of this into this operation, or this quantity, and that will be equal to, if we use the product rule, it will be the divergence of the product of the scalar and vector equation, so that's this term right here, minus the function f, which is right here, times the divergence of j. Now realize that we're doing a divergence with a prime, but it doesn't matter. We still use the product rule. And so we end up with primes right here. For steady state currents, you remember that the divergence of j is equal to the time rate of change of the charge density. But we have steady currents, so that's equal to 0. As a result then, if we take this quantity here, this is what we're trying to find, and we're left with this being 0 here, then this is the only term that's left. And so up here then we have del prime dot, and then here's our function, times j of r prime. We've only done the x component, but y and z are entirely the same. So let's just do the x component in terms of these integrals. We're now going to integrate over the final version of the derivatives and operations that we had, and that will be equal to the following. We have the divergence of this function here times j of r, and what we want to do is convert that to a surface integral. And so we have a volume integral, and we want to convert it to a surface integral. So if you remember, if you have the divergence of a function and you want to convert it to a surface integral, you can do that by taking the surface integral of the vector dotted into ds. When we're finished then, we have that the curl of b, which is equal to this quantity here, which is mu 0 over 4 pi, times the volume integral of j times the divergence of r over r squared d tau. We now want to look at this quantity here. Before we do that, we remind ourselves that the volume tau prime is chosen that it's large enough to contain all of the currents. So j on the surface, s prime, which encloses all of the volume tau prime, is always 0. So schematically, here's our volume and our surface s. All our currents are inside, like that. So what that means then is that the contribution, as well as the other two components of the integral of the same form, equals 0. So we end up then with one remaining term, and we have to look at this divergence of r hat over r squared. If we go back here, we're talking then about this factor right here. If we remember then that the divergence of these vectors here, this vector, is equal to 4 pi times the delta function in 3 dimensions of r vector. Given that, then we can stick that into the curl of B, and so we'll have our j of r prime times this quantity here, where we've substituted in for this divergence 4 pi delta cubed, and then that's integrated over d tau. If you then rewrite that in terms of these vectors, the thing to remember about the delta function in 3 dimensions is that you take this integrand and you look at this r vector here as being the difference of r and r prime, and you look at this function at the point where r minus r prime, which is r funny r, equals 0. So in other words, when r minus r prime equals 0. Well, what that means is you take this integral, you take the integrand and evaluate it under this condition here, which means that you just let r equal r prime. So what happens then is you have del cross B. Remember that this here is a function of r. We've changed the r prime by doing this integral with the delta function into j of r. So if you see here, we can cross out the 4 pi's, and we end up with this curl of B is equaling to mu 0 j of r. Well, this is Maxwell 4. Maxwell's equation 4. It's a general expression for the curl, and remember that this is the static B. This is B static at any point r, and so these are the field points that we're talking about. This equation here is known as the differential form of Ampere's law. So let's look at the integral form. Consider a surface S that's bounded by a curve C and is penetrated by a current density. If you were to integrate the current density over this surface, you would get the total current going through the surface. So we want to keep that in mind. And the way I've drawn this, the current density is coming up through and penetrating S and moving in this direction here. Remember, curve C is bounding the surface S. We integrate both sides of the curl, which we've shown is equal to mu 0 j, over this surface through which j flows. The curl of B integrated over that surface is just equal to the same surface integral except with this argument here. So we've just taken the original Maxwell 4 and integrated both sides in terms of the surface integral. The right hand side, as I said before, is related to the total current. If you take mu 0 out, the surface integral of j dot ds is equal to the current through that surface S. And we say then that because it's through the surface S, it's the current enclosed by that loop C times mu 0. The left hand side is a curl surface integral, and we can convert that to a line integral about a curve which spans the surface, which we've already shown was C, and so we have the left hand side given by this quantity here. So setting these two equal, we end up with the integral of B dot dl along the curve C is equal to this scalar quantity here. And it's a scalar because we're dotting two vectors together. So if you consider then this current basically creating a magnetic field, it's creating field at points along this surface. So let's simplify. Suppose you have C like this, and you have some wire like this coming up here. This is C, and this is the current I. This is the current enclosed. It's passing through this surface here, bounded by C. And what this current does is it creates a magnetic field all around this region here. You would expect then on this curve that surrounds the current that every point on here would have a B vector, and you dot it into the little elements of current, and that will give you B dot dl. You integrate those little dot products over the current C, set it equal to this, and you have basically a law which is the integral form of Ampere's law. If I is the current that is flowing through the region of space, in other words through S, bounded by the closed loop C, then mu 0 I enclosed is equal to the line integral of B around the loop C. What we're after when we use Ampere's law is a way to take this line integral and get some simple way to get b outside of the line integral so that we can find b. Again, this is called Ampere's law, and in the integral form, because we have an integral here, it was derived from the differential form, which is Maxwell equation 4. To ensure getting the right sign for the various vectors, it's important that you look at the direction of integration. You want to integrate around this curve in such a way that it's consistent with wrapping your right hand around the current. Your thumb is in this direction here. So if the current is coming up like this and you do the wrap around, then the direction that you want to take the integration is as shown here. So let me just read this to you. The direction evaluation of the line integral and the direction of the surface element, they're related, of course, it should be consistent with the right hand rule. Your thumb points in the rough direction of I, your fingers wrap in the direction of the line integration above. And so these arrows here are showing you that. Just to remind you, I enclosed can be a sum over currents. You could, for example, have wrappings of a coil, or you could have wires with n, I sub n currents, and that are penetrating S. So if you keep track of the flow, direction of flow, then the I enclosed is the sum of those currents. A statement about Ampere's law, it's always true, but it is only useful if you have symmetry, which enables you to pull B outside of the line integral. It's an analog of Gauss's law in electrostatics. Both of these laws require symmetry to be of any use. So here's some examples where the configurations that are easily done with Ampere's law are straight lines, planes, solenoids, and toroids. And we'll take a look at some of these. Let's take a steady current I that flows down a long cylindrical wire of radius A. And we're to find the magnetic field both inside and outside. And we'll look at three cases. The current flows uniformly on the surface of the wire. The current is uniformly distributed in the volume of the wire. And then the current is distributed in such a way that J is proportional to the radius S. Okay, so we'll take the case of the surface current. And for that, we'll take two Amperian loops, they're called. There's the C, so this is a C inside and this is a C outside. And the direction of current flow is in this direction. So here's our radius A, S less than A, S greater than A. Here's Ampere's law that we start with. And then we go through our symmetry arguments. The current is uniformly distributed on the surface. What that means is the current over here is the same as it is here, and so on. The cylindrical symmetry means that if we integrate this equation here, the B field can be considered constant for a given S, and so we just have B times the length of the line 2 pi S. Cylindrical symmetry says that if you spin the surface, does it change B? And the answer is no. So that's why you can bring this outside. If we have S less than A inside, what is the current? Well, all of the current is on the surface, and so there's no current enclosed. Again, all current is on the surface, and so therefore B is equal to 0 inside. So B times 2 pi S is equal to mu 0 I enclosed again, but now we're going to go outside, and so this should be outside, out. I enclosed is all of the current enclosed. If that's simply I, then you'll have B is equaling to mu 0 I, that's this term here, divided by 2 pi S, which is given here. This is basically what we would have gotten, which we did get with Biot-Savart, and so it's like an infinite wire. If we plot this, then what we have is inside we have B equals 0, and then as soon as we go outside it jumps up to this value here and falls with 1 over S, this 1 over S right here. So this is a plot of what the absolute value of B is, and the direction of B is given by the right hand rule. You'll have to point your finger in the direction of I, and your fingers on your right hand would point in the directions of B. So B are circles, the constant B values are circles that surround the wire and have the direction given by the right-hand rule. Now let's consider the case where we have a current that is uniformly distributed over the volume of the wire. So that means that every little area here has the same amount of current running through it for any position on that curve. We take the same Amperian loops, so this is C inside, this is C outside. Here's our law again, so Ampere's law. Because we have this cylindrical symmetry again, the integral becomes simply B times the area. So this is area right here for inside, and we'll have mu 0 I enclosed. So if we're inside, we'll have I enclosed being equal to I times the ratio of the area of this curve to the area of the wire. That will be equal to I total times the ratio of areas given here. Another way of looking at this is I enclosed is equal to the current density times the area. So if you look at the current density, because it's uniform, it's I over the area of the wire, and then the area of the surface that's enclosed by C is pi s squared. Same thing. Solve for B, and so you have mu 0 over 2 pi s times the current, and the current is equal to I times this ratio here. Finishing it off, mu 0 I s over 2 pi a squared means that B goes as a linear function of s. Let's look outside, so we start with the same equation. The symmetry allows us to bring B outside and integrate over the area. We have s greater than a, and so all of the current is enclosed by our loop C. We end up with the same result as we got for A. B is equal to mu 0 I over 2 pi s. Again, it's like an infinite wire. And so here's the plot of that. So we have the linear plot here. So B is a function of s in a linear manner, and then it falls like an infinite wire equation out here. The difference between the other one was we had zero current here jumping up to here, and here we have a function that comes up to this point and then falls as you go outside. Suppose we have a constant, forgive me, I called it K. This is just a constant times S. So our current density is linearly increasing with S. So it's 0 at the origin and increases out here until you hit A, and then it stops. So again we have our two C's, one is inside, one is outside. Here's our Ampere's law, and if you think I'm cutting and pasting these from previous slides, you're correct. Because of the uniform nature of the distribution of currents, with the cylindrical symmetry, we can bring the B outside times the area that we're subtending. So that's this area right here for inside, and that's equal to mu 0 I enclosed. If we start with s less than a, we have to do an integral. We take the differential of current enclosed at the radius s is equal to the current density at s times a differential of area. So here's what I'm talking about. See, we're integrating basically the current density over this surface here. If you take the surface and divide it into rings like this, where this is s and this is ds, the area of this ring here would just be 2 pi s ds. That's the differential of area, and we multiply that by j of s. Here's j of s, here's 2 pi s ds, which is the area of this little ring here. And so we simplify this, 2 pi k s squared ds. So to get the total current that's passing through this surface here, we just integrate from 0 to s, the differential of current that we got up here. Putting that in, we have 2 pi k times this integral. That just gives us 2 pi capital K over 3 times s cubed. So then go back to our Ampere's law to get B, and so B will be equal to mu 0 over 2 pi s times the I enclosed, which is 2 pi k over 3 times s cubed. You get a factor of s and s cubed where you can cancel, so you get an s squared. So this goes up as s squared. Now we do the same thing. Here's Ampere's law with our symmetry argument to get B outside. We have s greater than a, and so in that case here, all of the current that is being transmitted down this wire is equal to I enclosed. so all current is enclosed. So this is 2 pi k over 3 times A cubed. So put that into this equation here. So this would be I total right here. Solve for B, and we end up with an equation that looks very similar to 1 over S, which is the equation for an infinite wire. So as expected, it has the same S dependence as A and B if you're outside the wire. So here's the plot of this function. You go up as S squared, so it has a little bit of curvature, and then as soon as you go outside, you go back to the infinite wire type behavior. To get the direction of B for all of these cases, I mentioned this before, you use the right-hand rule. If you're looking down the wire towards the opposite direction of the current, so the current is coming directly at you, then if you use the right-hand rule, if you're inside and it's not 0, then you'll see the streamlines of B being these circles heading in this direction. Because you put your thumb out of the page to indicate the direction of the current, and your fingers wrap in this direction. If you're outside, then you do the same thing. All of the current is flowing in the wire. You have a total current here, or put your thumb in the direction which is out of the page, and that gives you the direction of the streamlines for B. And that's true for all cases. In both cases, the B lines close upon themselves, which is consistent with the divergence of B equaling 0. This beats this to a pulp. I enclosed can be a sum over currents, I sub n, and we said that it would be the sum of the currents. Anticipating collections of currents like coils that are all of the same magnitude, we first realize that if a single current passing through S bound by the loop C occurs, then if this is the surface S, here's C, here's the single current I, then we know that I enclosed is equal to I. Ampere's law, you just put this equal to I. If you have the loop enclosing several currents, let's suppose they all have the same magnitude, but some are flowing up and some are flowing down. Number going up is n up and the number down is n down. Then the I enclosed by C is equal to n up times I plus n down times minus I because of the difference in the direction of current. That will give you the case where you have both plus and minus types of currents of the same magnitude flowing through the surface. Normally you have a condition where you have capital N currents of magnitude I, and they're all flowing in the same direction. And obviously you would not have this term, you would just have this term. For example, out of the page you would have I enclosed by C is equal to capital N times I. So these are all flowing in the same direction, and so you just get a total current that's equal to N times I. So here's an example where we need to use that, and that is a sheet of current. It has a current density capital K, and we're to find the B field on both sides. So let's take K in the plus direction as I've shown here. So all these vectors here represent flow of charge, positive charge. We're going to view it as a linear superposition of parallel line currents coming out of the page. So here's the plane of charge flow. And the dots here are little elements of current coming out of the page right towards you. And so we'll represent then a continuum of charge flowing as these little tiny spaces. If you look at just a few of them, so you just take a few of these, I want you to look at the B fields. So we know that a single wire has the B fields. If it's coming out of the page, the circulation of the B would be in this direction here. Now if you put another one, another one, another one, another one, then what you have are opposing B fields here. You have basically unopposed up here and here, and so on. So you have 0 field, 0 field, 0 field, but up here all of these are adding together. The spacings are very small. This will add up to a uniform B field, in this case in the negative y direction. Okay, here's our axis. Y is this way. These are coming out of the page if we're looking this way, and so the B field on the top is in the negative y direction. This is just basically the right hand rule applied to spacings that are very small and uniform. Well, I think you can see that the B field on the bottom, see, would add up in the opposite direction. So here are the B's in the plus Y direction below the sheet of current. So that's how you get the direction of this, and how you would argue that because these are all the same, you would end up getting a uniform B in those directions. Let's assume then that it extends infinitely in the XY directions. B is in the direction that is shown, so here's B on the bottom, here's B on the top, and we're going to consider that to be uniform and independent of Z. That is a result of having this infinity in the XY directions. The analogy would be a charge sheet where if this is infinite, then you don't have any Z dependence of the E field. We choose a loop, which is this curve C above, and we let it go above the current sheet and down below it. So this is supposed to be below the current sheet. The current sheet is flowing in between these two surfaces here, or there's these two parts of the loop. So what we're going to do is, because of the direction of the current, we want to use our right-hand rule to get the best guess of what direction we're going to integrate. If we put our thumb towards the direction of K, then our fingers would wrap around C like this. That's the direction to try. So here we go. Here's Ampere's law, just like we used before. Because this is a constant, we can bring it outside of the loop, and it will have two components. It will have the component along this part of C, it will have a component along this part of C, but because these are normal to B and normal to the current sheet, there's no contribution to B along here. So we're only left with the terms where we're looking at B parallel to the direction of integration, and of course parallel here. So as a result, they both contribute with a plus sign. So this is the left-hand side, and then the right-hand side has to do with the current that's enclosed. Now remember what K is. It's the current per unit length in the Y direction. And so if you take K and multiply by L, you get the current that's enclosed by this surface here, and therefore enclosed by the curve C. So you add these together and solve for B, and you get the magnitude of both top and bottom equaling mu 0 K over 2. Then you go back to the direction of B that we talked about before, and so you can go through the right-hand rule again, that the B on top is heading in the negative J direction, and B on the bottom is heading in the plus J or plus Y direction. And these of course are for Z greater or less than 0. The lack of Z dependence is similar to the lack of Z dependence for the E field that I've mentioned above an infinite sheet of charge with uniform charge density sigma. Suppose we have this sheet of charge with density K, and we put a line current that I show here that is directed along the x-axis in the negative x direction. On the top, if this is above the plane, our B is heading in the negative y direction. And this line current is a distance d from the sheet current plane. B is constant, does not depend on Z, so for all Z we have this B here. What is the force on the line current? Well, we take a dl along the along the line current, that's our dl. We have a current flowing through there, and it's interacting with this B field. So the df on the line current is given by this. dl is along the direction of the current in the line current. So if we divide by the magnitude of dl, this will give us the force per unit length. We can't find the force on this because it's infinite. It has an infinite length, so we can only find something that is a finite length, and so we'll just take it per unit length. Our result will be a vector with the units of force per unit length. We've taken the magnitude of dl and put it here, so what we're left with is a unit vector. That's the unit vector dl. And if we multiply that by I, we'll just call it the vector I. Magnitude I with the direction of I being given by the unit vector along the current direction. So we cross that into B, take into account that our I is in the negative x direction, our B is in the negative y direction, so taking that cross product we get B times I, and that will turn out to be in the z direction. So as a result of putting current through a wire near a current sheet, we end up with a repulsive force whose magnitude is given here. So here's the vectors. Here's I along this direction, here's B here, and then I cross B is this vector here. Let's look at a solenoid, and I've stretched it out here to show you what it looks like. This image, by the way, comes from NDT. Think of the solenoid like a flat sheet current that's flowing around in this direction here, going in a circle. However, if we separate the windings, we can see the direction of the B field. Namely that each wire has a circular B associated with it, and the same thing goes where if we're below or above, then the tendency down here is to have B fields in this direction. Up here we might have some fields in this direction. Although it's not obvious, the density of these streamlines is small up here compared to inside the coil. There's lots of cancellation in the vicinity of the wires, and B is nearly uniform inside the coil, and outside B is small. If we take these wires and space them as small as we can, and make the length of this very long in both directions, then what happens is that the B field becomes uniform inside. It does not depend on the radius. So let's take a more idealized solenoid, namely one that's infinitely long and where the spacings of the wires are very, very small. Under those conditions, we can assume that inside the B is uniform, and that B outside is equal to 0. So we'll take this curve C that encloses some of the windings, integrate about this path that we show here, where we have sections that are perpendicular to B. Over here we have a section which is in the B field, and we have 0 B field up here. So that's going to help us simplify the integral. If we let little n be the number of turns per unit length of the coil, then if we take a distance h, the number of turns that are coming through that loop is equal to little n times h. If each one is carrying a current I, then I enclosed is equal to I times n times h. Now let's consider a portion of the integral. So we're integrating around the loop, and so we're considering b dot dl, and so dl is a little arrow going in the direction of integration on this curve C. First we just take the end parts here, and what we have is that B, which is in this direction, is perpendicular to the path, the dl's on this part here. So that means that those will contribute 0 for that part of the integral. So this part here and this part over here give us 0 contribution. So what about out here, C and D? Well, B is 0 out here, so that gives b dot dl equal to 0 again. Finally, we go to the non-zero contribution, which is here. So dl is parallel to b. The integral then will give us a non-zero value over this direction. Coming down here, oh yeah, this should be L. b dot dl is equal to, okay, b is a constant, and so b comes outside. The integral of dl is equal to h. That's equal to mu 0 I enclosed, which is equal to mu 0 I nh, because that's the current that's enclosed. So you can solve for b. You'll have mu 0 times I times n, which is the ideal solenoid equation for very tight windings and infinitely long in length. Another simple case is inside a toroid, a real solenoid that we were looking at before. The B field sticks out both ends and spreads apart and weakens at the ends. One way to avoid that is to bring the ends together. And that what we mean that is we wrap our coil around like a donut, so shown here. It has no ends, and we call that a toroid. Here we're looking at the current coming out of the page and into the page for wrappings around this volume here. And we're assuming vacuum or air for this media in the region here. To find the B inside, we take a loop at some radius r from the center of the toroid. That's this curve here. If the coil has a total of n turns, capital N, then if you take this C, it's going to enclose capital N turns. And therefore the enclosed current is N times the current through one of the wires, which is obviously the current through all of them. So the enclosed current is just N times I. So here's Ampere's law, and again this is our L, and we can bring B outside because it's constant along this path. The length of that path is 2 pi r, and that's mu 0 I enclosed, which we've said is mu 0 times I times N. So again, a simple equation, solve for B, and so inside the toroid we have this function for B. Notice that it depends on R. So it is not a constant over this cross section here, and it actually has an R dependence as you go around here. Now if this is small, you'll have an average value that's just going to be given by the R of the toroid. So for R large and cross section small, the B can be considered uniform. Just to get the direction of the B field, consider a coil as part of this. So think of this as being large enough R that you can almost think of it as a coil. And we've already shown how to get the direction of this kind of coil. And so if we put it up here, you'll notice that the current is coming out of these windings and going in here. You might not be able to see it, but that's the way it is up here. Coming up here, we're coming out of the paper or page, and here we're going in, just like this section of the wire. So the B field is in this direction, which means in this direction here. So that's how you would deduce what direction the B field is for this particular arrangement. The other way would simply be to take one ring, so consider the field due to one ring, and we've talked about that before. So if you have current going this way, right hand rule gives you a B field in that direction here.